Thank you. So it's my great pleasure to present to you some of the work that we're doing on computational imaging, programming light matter interactions for information processing in specific. I'm sorry I couldn't be there. Hopefully next time. From the crowd, I can see it's a very exciting and successful conference. Congratulations. And on a Sunday morning, I salute you, your motivation to come to this seminar and the conference. So thank you. So this talk is about some of the work that we have been doing on programming light matter interactions. So I'll talk about diffractive networks or diffractive optical networks, diffractive deep neural networks interchangeably used. This is a framework where you can structure light matter interactions for performing statistical inference with light. It's also a great platform for computational imaging and also inverse design. So throughout my talk, I'll give you examples of these different capabilities enabled by diffractive processing of information or diffractive networks. So a diffractive optical processor is composed of structured layers. For example, this one is a diffractive processor operating at terahertz wavelengths. Each one of these layers contains some surface roughness, as you can see in here. These are controlling the phase of the light that is transmitted, the terahertz wave, and there are approximately 0.2 million diffractive features here that are optimized for a task. So in the visible near-infrared parts of the spectrum, these kinds of processors would be as thin as a stamp, so maybe 0.1 millimeter, 0.2 millimeter in total thickness. The design of a diffractive processor is done in silico. So you use deep learning-based optimization, task-specific optimization. And once we're done with the design, once we optimize the phase features of each layer, one following the next one, we fabricate these and form structures that compute with light matter interaction. For example, you can design a diffractive processor, diffractive network that can classify objects in front of it by routing the photons to a predetermined detector that is assigned to a class. Rather than creating an imaging system and classifying the object, you can actually have new objects here, never seen before, that can be classified based on the maximum number of photons that the diffractive system routes to the back focal plenary. Some of the major advantages of diffractive processors are the following. First of all, you're computing with light matter interactions through passive layers. And these are very dense in the sense that the layer-to-layer separation is a few wavelengths or a few tens of wavelengths, depending on the design. So which means these are low-power processors. They also have extreme low latency. In a few tens of picoseconds, you get the result of your computing. And they're scalable. You can fabricate them over larger areas, larger apertures, and form diffractive processors. This one is a handwritten digit classifier. Most of what I'll share with you today is a coherent diffractive processor that is based on spatially coherent illumination, but you can also have partially coherent or incoherent diffractive processors depending on the task that you want to achieve. In this example that I'm sharing with you, the diffractive processor is routing, for example, never seen handwritten digits before as the light penetrates through them to the correct detector, as shown here, for example. And this information encoding can be done in different ways. Because these are coherent processors, you can encode the information in the amplitude channel. For example, these are never seen handwritten digits before. For example, this is a never seen number 8. At the back focal plenary, this part received the most number of photons, and that's where we allocated class 8 detector, and that's why you get the correct classification. So these kinds of processors can reach for MNIST close to 98% classification accuracy. And because these are coherent processors, I've emphasized, there's another very exciting way of encoding the information at the input, and that is the phase channel. We've also created different types of classifiers. For example, this one is a fashion product classifier based on the Fashion MNIST data set. It's also composed of 10 different classes: sneakers, trousers, bags, etc. And the rule of the game is to generalize to different classes of objects, not memorize them, because everything that we're testing here is actually a test object never seen by the network before. These are some experimental results from phase-encoded objects. These are never seen objects before. For example, this is a dress never seen before. Most of the photons went to this detector that is pre-assigned to class 3, so on and so forth. In fact, phase encoding is a powerful way of bringing nonlinear encoding to a linear diffractive processor. So if you want to read more about how you can extract more information about a diffractive processor and phasing encoding, you can actually refer to this recent paper of ours. Phase encoding is a nonlinear form of encoding, which means at the output field, you don't have linear combinations or different phase input objects. That means if your input aperture that you would like to process contains phase information by default, that's perhaps the best way of bringing better inference, better computation power through diffractive processors. I'll give you a good example of this with this phase conjugation example. Optical phase conjugation is arguably one of the most important, influential, nonlinear operations that for decades optics community has been obsessed with for many defense-related applications, optical microscopy, sensing-related applications. It's a nonlinear operation, and that's why the last several decades used nonlinear crystals, four-wave mixing, Chi3 processes to build optical phase conjugators. We've shown that you can actually take a linear diffractive processor and program it by shaping all these diffractive features collectively to do phase conjugation, so that the phase aberration here at the input can be conjugated at the output accurately if you design all these features and optimize them through deep learning-based stochastic gradient optimization. But different than nonlinear crystals, this is a very highly diffraction efficient solution, and it can work across a large bandwidth so that you can actually have the same diffractive processor to perform all optical phase conjugation at many wavelengths at the same time. For doing this, we've trained the diffractive features here successively through some examples of different Zernike polynomials at the input aperture. These were our training sets. And all these features here were optimized till you get at the output a beautiful phase conjugated field. But once the training is done, we've tested the system with more complicated aberrations, more complicated phase structures with many different Zernike polynomials. And the results are showing actually some beautiful generalization. Even though it's trained with a single Zernike polynomial at a given time, it actually generalized beautifully well. These are the all-optical diffractive network outputs, nicely matching the target phase conjugated fields. And these are showing you the error maps in phase and amplitude, showing you the success of the system. In fact, external generalization is shown here. This is where you train a network with a single Zernike polynomial at a given time, but when you test it with several different combinations of different orders of polynomials, it still works beautifully well, which tells us that it's actually not memorizing, but generalizing to do all optical phase conjugation as desired. These are also experimentally tested with a 3-layer diffractive processor optimized, again, using stochastic gradient descent. These are the designs of these diffractive layers that we converge, and these are the fabricated ones using 3D printing, and this is a terahertz setup. To test the phase conjugation idea along the optical path, before the all-optical diffractive OPC network, we put some random diffuser, and we put the same random diffuser after the network so that if the phase conjugation is correct, all-optically performed correctly, the same input aperture will be nicely matched at the output. So showing you that really we have a phase conjugation operation experimentally validated as shown here with different types of random phase perturbations along the optical path. If you don't do any optical phase conjugation, you will get some random beam at the output aperture. With phase conjugation all optically performed through these 3 layers, you get what you want. In fact, we've also shown that the same diffractive processor can do phase conjugation at 3 distinct wavelengths at the same time, as shown here with the output beam nicely matching the input aperture with different random phase perturbations, kind of like undoing the impact of random phase perturbation plane along the optical beam. You might be wondering here if we use a spatial material with some dispersion engineering to achieve phase conjugation operation at 3 distinct wavelengths. In reality, we don't use dispersion engineering. In a Gedanken experiment, you can even use flat dispersion for the material because the dispersion that we're using is the phase kernel of free space. That's beautiful in the sense that you can actually, even with a material that has flat refractive index across different wavelengths, this kind of a feature at different wavelengths, the same task can be repeated. These solutions are also quite efficient in terms of the output diffraction efficiency. As you can see, you can achieve more than 80% diffraction efficiency. The rule of the game to improve performance, reduce error in phase and amplitude, while at the same time retaining this diffraction efficiency advantage, is deeper architectures, which means this diffractive processor in general, the architecture itself, likes depth, which means deeper architectures can always find a better performance and a better diffraction efficiency at the same time. So if you're hungry for both performance and diffraction efficiency, deeper solutions with more diffractive layers would be the preferred solution. Of course, if you can fabricate and align them. So this was a good example of how you can take a linear diffractive system and perform nonlinear functions thanks to spatially phase encoding at the input. And we've been playing with this platform for various different applications, all the way from quantitative phase imaging, which means taking a phase object and transforming it into an intensity quantitatively, kind of performing holographic reconstruction and QPI at the same time through a diffractive processor, which also is a nonlinear process that you're approximating with these diffractive processing schemes. Arguably, it's also a beautiful platform for sensing. For example, if you're looking at defects within a body of volume, within a structure, let's say, diffractive processors can also be very powerful to catch these hidden defects, unwanted objects within a volume. And recently, we've demonstrated basically rapid sensing of hidden objects with a single pixel terahertz diffractive system. Different than visible wavelengths, of course, terahertz has some unique properties, one of which is to be able to see through clothing packaging. Think of a problem where there's a packaged product like a pharmaceutical. How do you know if there's a defect without opening it? That's exactly the kind of problem that we're addressing here. And we trained an encoder and a decoder composed of diffractive layers to look at defect detection without creating a 3D image of a volume. And this is done through a single pixel, so you don't need to actually look at scanning or creating an image out of it. And here we're operating with 2 different wavelengths and programming these encoder-decoder pair to understand defects. If one of the wavelengths is larger in the single pixel output, it says there's a defect. If not, there's no defect. You can think of this as a spherical wave detector, which means unwanted spherical waves due to defects are detected through this scheme by converting spatial features into spectral features. This was tested with basically 4 diffractive layers, 2 of which are working as an encoder, 2 of which are working as decoder. And we looked into defects in silicon. So not visible because it's an opaque system, but terahertz waves can penetrate through. And we purposely created structures that are hidden, but that contain defects, and some of them not. By looking at the single pixel output through terahertz, we were able to detect these defects accurately and through a single pixel without scanning. Hopefully this gives you a good idea about the capabilities of diffractive processing, not just for classification, but also in this case, sensing of unwanted defects without opening the package or without opening the system. Diffractive processors are also great for computational imaging. It can solve, as a platform, diffractive processors can solve inverse problems. And I'll give you a good example of it, how you can program a diffractive system to act like a super lens that can solve some of this inverse imaging problems as light is penetrating through a diffractive processor, and in a few tens of picoseconds, you can get your answer. And the problem that we'll be tackling here is going to be the following. Let's say you have an unknown object that is completely hidden behind a random diffuser. The object is changing constantly without your knowledge, and at the same time, the random phase diffuser is also going to be changing without your knowledge. And we want to build here a diffractive processor that's going to stabilize the image reconstruction in a few tens of picoseconds. As the scattered light goes through this diffractive system, we wanted to see at the output plane the image, which means without any digital computing, all through light matter interaction, if it's safe for your eye, we want to see the result. In other words, we're solving this problem as highlighted here. Objects are going to be changing, sometimes out of distribution. The diffuser is dynamic, random. If you don't do anything, you'll be left with these speckled patterns, which you can, of course, use a digital computer and perhaps a neural network to reconstruct them. But we don't want to do that. We want to get the answer to a good degree with just a few tens of picoseconds of light matter interaction. To be able to do this, we show thousands of examples of random diffusers along the optical path and random objects. So during the learning process, there's a couple of thousand of these random phase diffusers that are distorting the objects. And these diffractive layers at half a wavelength pixel pitch, at the diffraction limit of light, they're being shaped constantly based on the error at the output plane, structural error, so that at the output, we want to converge to the image of the object that is at the input, despite the presence of these random diffusers. And this shapes the evolution of the diffractive processors that are kind of like tightly packed, one following the next. Once we're done with training, we fix the diffractive layer. There's no more learning. And then we start to show new objects and new random phase diffusers never seen before. For example, these are diffusers that are having a capital B right next to them, B1, B2, B3. These are blind diffusers, and these are blind objects, which means they're never seen before. And a good signature of a competitive solution is it will work with known diffusers, K, which means these are the diffusers that are used during the learning, and B refers to new diffusers never seen before. A good diffractive processor will achieve the same level of reconstruction as some of the known diffusers. In fact, there's some beautiful physics. It's not just random optimization. You can get some inspiration from how this solution space is evolving. If you look at the diffractive layers that give you this kind of performance, one layer following another layer following another layer. If you look closely, you see that there is a microlens array that the diffractive system is evolving into essentially a sparse microlens array. These are axially aligned from the first layer. If you shoot a ray, it's going to go through the next layers and hit the microlens. So these are axially aligned set of microlenses that are packed together, and that they form the backbone of the imaging system. However, they're not sufficient. There's also a phase code that is evolving, optimized, one layer following another layer, and that phase code is actually acting like a three-dimensional filter that filters out the garbage. That means, depending on the complexity of the problem, these microlenses are evolving, and together with the features around them, they mitigate the impact of the random diffusers and give you an image. If you just retain the microlenses and erase everything else, like these, for example, you can't reconstruct. For example, in this example shown here, with this kind of a random diffuser never seen before, if you erase the code around the microlenses, you get nothing. You get a speckled pattern as shown. It's the collaboration between the microlenses and the surrounding phase features that make this system work effectively. And depending on the complexity of the problem, the correlation length of the random phase diffuser, these microlenses can come together in a denser manner. For example, here, the correlation length is larger. So they are densely packed because you don't need as much filter function between the space. That's why the resolution here is higher compared to some of these other solutions. So it's this symbiotic relationship between these evolving microlenses and the filter function around them that give us this unique capability to generalize to never seen objects and never seen diffuser combinations. In a follow-up work, we've actually transformed this system into a single pixel classification system in the presence of a random diffuser. Here, the idea is to take the spatial features of unknown objects of different classes and convert them into spectral fingerprints coming from a single pixel detector. This way, actually, we built resilience against the changes of the phase diffuser. If you don't do anything smart, at different wavelengths, this is what you will get through a random phase diffuser. But by encoding the spatial features into a fingerprint across a group of wavelengths, we were able to actually look at the single pixel spectrum and classify the object based on the wavelengths and their intensity, the maximum intensity assigned to a certain class of object. That gave us actually a beautiful way to be accurate through a single pixel detector, despite the presence of random diffusers. With new diffusers never seen before, for handwritten digits, we were able to achieve approximately 88% testing accuracy. And this system actually does not overfit to the presence of diffusers. If in the testing phase, you take out the diffusers completely, during the training, you've always shown the objects through the diffusers. But for the first time, you're taking diffusers out. The accuracy actually jumps to more than 96% classification accuracy for test handwritten digits. That tells you that this is actually physically learning how to do spatial feature to spectral feature conversion through the diffractive processor that's broadband in this case, and it's not overfitting to the presence of the diffusers. So there's some beautiful physics behind these systems that help us perhaps design some new instrumentation, whether it's endoscopic characterization, spectroscopic characterization of specimen for different parts of the spectrum. The results that I've shown you so far, they were mostly basically a diffractive processor as an analog computer helping your imaging or sensing task. But equally exciting for me is the collaboration between digital networks and diffractive networks. So this is kind of the best of both worlds, how to integrate programmable diffraction to collaborate with digital networks. Sometimes diffractive networks will be working as encoders, and sometimes they will be working as decoders for diffractive systems to collaborate with digital networks. So I'll give you some few examples of this before I conclude. In the first case, we'll start with a diffractive network acting like an encoder for a digital network to decode the information. A good example of this actually is one of our recent work on information hiding cameras. In this scheme, we have a diffractive physical processor. Again, in the visible near infrared, you're looking at as thin as maybe 50, 100 microns thickness, very thin optical components where layer-to-layer separations a few wavelengths. The task of this diffractive processor is to take any arbitrary message and transform it into a dummy-looking ordinary message that might mislead us, but there is a back-end digital network that is jointly trained with the diffractive processor so that the back-end can retrieve the original image, even though it looks boring for our own eye. So we optically conceal the object information into ordinary images to deceive the human observer, but pass the information of interest to someone who has a jointly trained electronic decoding network. So this system is trained with lots of examples and, of course, blindly tested. And there are different kinds of loss functions because first, you need to be careful about how the images look, because the images, despite the inputs that you have, the images should look like ordinary, dummy-looking objects that you set and you deceive the observer. And the CNN, the backhand convolutional neural network, will be panelized until it reconstructs a distant representation of the original image. Through this process, you're training the coefficients of the convolutional neural network, and you're training the diffractive features, phase features of these, in this case, 5 layers that are successively put together. So they know the presence of each other. This kind of a scheme can be made fairly tolerant to errors if you vaccinate the learning by injecting noise. For example, if you look at this design, as you change the input and add noise to the camera, the CNN is still robust. So this system is trained with added noise during the whole learning process. That's why the failure of the backhand happens only after a significant injection of noise to the camera system. So you can also make them resilient. And a beautiful feature of this system is the fact that you can use multiple wavelengths to encode different messages through the same diffractive processor to give you a boring image. In this case, for example, at 3 different wavelengths, let's say red, green, and blue, you have 3 different messages. At the output, no matter what the combinations are, you will get the same boring number 8, but with just color changes. And at the backhand, you can reconstruct all these 3 images at the same time. For something like this, again, you do not need dispersion engineering. You can also have the same refractive index at all these wavelengths that you use, because we do not rely on material dispersion engineering. We rely on spherical waves, transmission dependence on the phase of the spherical wave that depends on the wavelength. That's essentially how this whole system is being able to do different tasks at different wavelengths, not through material engineering. We've shown this with a single layer diffractive processor that is communicating with a backhand convolutional neural network. This was the design, and this is essentially what we fabricated. These are experimental results showing you some distant reconstructions at the back end, kind of showing you the capabilities of the system. We've also pushed this for visible wavelengths in another form. This is reflection. We call it lying mirror, which means you have different inputs in here at the output in the reflection system. Through this diffractive scheme, we have a boring image. No matter what kind of an object you have in here, you get the same lying mirror. And we've also made it rotation, shift, and scale invariant by feeding during the learning process various objects at different rotation angles, at different shift amounts, at different scales, so that the system actually is resilient to that. Using some spatial light modulators, we also demonstrated this experimentally in the visible part of the spectrum. And it's actually fairly broadband, more than 60 nanometers almost. You can have a decent performance. This is our training range within which the correlation coefficient to what we want is fairly good. But even outside of the training zone, it performs very well, as shown here with these experimental results in the visible. Another opportunity here is to switch what the diffractive processor does and what the digital network does. In the previous example, diffraction or diffractive network was an encoder. You can also switch the roles. You can have a diffractive system to work as a decoder for a digital encoding scheme. A very good example of this is actually learning to communicate around an arbitrary opaque occlusion. Think of this major problem that has, of course, Department of Defense or security-related applications. Think of this major problem. You have an aperture and you're constantly sending some messages to another aperture. Let's say you're in free space. And this free space communication link is working beautifully well. But then suddenly an occlusion appears between your aperture and the receiver. And there's no wall that you can bounce the information off a certain mirror or wall and bypass this occlusion. You're in free space and you cannot send any direct light from your aperture to the output field of view. How can you build a system that can use the occlusion against itself? That's essentially a message here of the collaboration between diffractive networks and digital networks. You take an arbitrary message. I'll start with some simple examples like handwritten digits, but I'll show you how it generalizes to any arbitrary message. Start with a message. This network is an encoder digital network that takes these messages, arbitrary messages, and creates a unique phase fingerprint for it. So this is kind of like what you put on the spatial light modulator, whatever you want to pass, except you take the messages and convert them into phase signatures. These are not random phase signatures. These are optimized so that they can communicate with the edges of the occlusion and create secondary spherical waves that represent the message of interest. So essentially that phase encoding is communicating with the edges of the occlusion to radiate through scattering to a diffractive decoder to reformulate, reconstruct the original message of interest. So this is the communication between a digital phase encoder and a diffractive decoder to retrieve the original information. Look at this, for example, movie, which highlights the entire story. You have different types of messages, each of which is uniquely represented by a fingerprint of phase. This phase pattern after free space propagation faces the dynamic occlusion. It's scattered through its edges to be decoded by a static diffractive processor, which gives you the reconstructions in a few tens of picoseconds. As the occlusion is dynamically changing, its topology is slightly changing, you can see that the message is slightly varying, but reconstruction is stable. So you do not need to even know exact topology of the dynamic occlusion. If you don't have this whole scheme, this is what you get. It's a perfect lens. Because of the occlusion, you just see almost nothing except the scattering from the edges. This also works for a bigger occlusion, as shown here. For a bigger occlusion, resolution at the reconstruction degrades because now you have to work with basically weaker spherical waves scattering through the edges, and their perturbations limit the resolution, but still you get a distant reconstruction for these messages as a dynamic occlusion that's bigger is oscillating. Again, without any smart encoding decoding pair, a perfect lens would see nothing because of the 100% absorbing occlusion. The interesting thing here is that you train this whole system, encoder-decoder pair, with simple letters, handwritten digits. But for the first time, you give complicated objects from ImageNet, let's say. These are, trucks, different kinds of objects, never seen before and out of distribution. It works beautifully well. As you can see, a perfect lens would see, again, nothing, depending on the occlusion size, and the decoder beautifully reconstructs these out of distribution objects, which means it's perfect external generalization on types of messages never used during training. These systems can also be made diffraction efficient. If you are after diffraction efficiency of the whole process, you can, of course, sacrifice some performance in the reconstruction plane in favor of diffraction efficiency. For example, this solution here was panelized for diffraction efficiency, and you have almost 53% diffraction efficiency with some sacrifice in reconstruction, all-optical reconstruction resolution. If you're really after resolution, you have to sacrifice diffraction efficiency to almost 0.7%. In general, this kind of a signature is highlighting performance, diffraction efficiency trade-off. And you can engineer the loss function of your learning depending on where you want to be in terms of diffraction efficiency or reconstruction fidelity. If you want to push this curve outward, you can increase the number of layers. So this is a typical fingerprint of diffractive processors. We tested this idea experimentally. For example, this is a square occlusion metal object here, which with, in this case, a single diffractive layer, we were able to reconstruct it. As shown here, these are experimental results, nicely matching our simulations to show you that you can do spherical wave engineering through a digital encoder to bypass a completely opaque occlusion. It also works for different types of occlusions, as we've shown here experimentally. These are fabricated occlusions. This is a random occlusion that deviated from a circle. Even then, you had some distant reconstructions, as shown here with our experimental results at the back focal plane. In the last couple of minutes, I'll finish off with another exciting application of this collaboration, where, again, the idea would be digital encoders compressing the information, helping us reconstruct information through a diffractive decoder. This time, we will be looking into optical generation of images from random noise. So these are optical generative models, where by feeding random noise to a system that has a digital encoder, we'll be creating new objects following a certain data distribution, but generating content, novel content never seen before, through a process that distills information through a diffusion model. So the idea here is to create a snapshot student optical generative model that learns from a teacher. The teacher here is actually a standard diffusion model, which is trained to take noise and create novel images through maybe 1,000 steps of the diffusion process to create new images that follow a certain distribution. It links, basically, it trains a denoiser network to take noise in small steps, denoise it, denoise it, denoise it, and then add some random noise at every step so that you get a beautiful generated image. Now, that's our teacher, the standard diffusion process, with which we train an encoder, digital encoder, to take the same random noise and convert it into a phase signature at an SLM, spatial light modulator, so that a static decoder, diffractive decoder, can generate the image and decode it so that you can get a snapshot student optical generated model giving you new images. We have tested this idea with different kinds of schemes. Initially, we generated, for example, this is how the system works. The spatial light modulator here is communicating with the shallow digital encoder. This is the distillation process from a diffusion model. So there's no diffusion here. The digital encoder is a snapshot process. It gives you new spatial light modulator patterns, phase patterns here, which are decoded and then captured by this image sensor. We've shown you can generate with a very compact snapshot encoding process with, let's say, 3.6 million parameters, some beautiful handwritten digits never seen before. These are not human generated. These are generated through noise. Same idea here for a different student model, snapshot generation of new fashion products. Again, never seen before. These are created from random noise passing through a shallow digital encoder, which has about 3.6 million parameters, and then everything else is done with a static decoding layer, which is also a spatial light modulator that's reconfigurable. From toss to toss, you can change it. We've shown that the generated content is following the target distribution. So which means from the perspective of classification or from the perspective of diversity of classes, recognizable image generation, we see that it's on par with the original data set of handwritten digits or these fashion products. So the generated content appears to be following the same distribution. We see the same architectural advantage. Our generation gets more effective, more diverse, more recognizable, and more diffraction efficient if you have a deeper static decoder. So that's why this curve here is getting better with orange, with 5 different layers working together at the decoding end. We also expanded this platform to higher resolution image generation. The previous results were relatively lower resolution and smaller field of view. We expanded them into several millimeter wide image generation following Van Gogh distribution. So these are showing you the teacher diffusion model results after 1,000 steps. This is the optical students' numerical results and experimental results. What you see here with the orange box, these are examples where the snapshot optical generated model here disagrees with the teacher. So we distilled the information, but as you can see, the student optical model does not agree with the teacher. So it's a good indication of learning image distillation and still being able to generate unique content, not just memorize or playback the diffusion model that is a teacher. In this case, we were using 580 million encoding parameters. So the digital encoder is snapshot, but it has significantly larger number of parameters. These are some of the other examples from experimental results, nicely matching the numerical optical forward model, and sometimes disagreeing with the teacher, sometimes agreeing very well with the teacher as expected. You don't have to use always a beefy encoder. We have also used significantly smaller number of parameters. In this case, we're using 85 million parameters in the encoder scheme. It still works beautifully well. In fact, you can even go down to approximately 40 million. For example, this is a 44 million digital encoder snapshot, giving the information back to an optical decoder to reveal these images as shown here. All of these are new content following the style of Van Gogh, created from random noise that's never seen before. By using red, green, and blue illumination in sequence, we were also able to generate these colorful images that also sometimes deviate from the diffusion model, but sometimes agree very well with it. To emphasize, a digital diffusion model is using here about 1 billion parameters, but more than that, it's got 1,000 steps as part of this iterative denoising process. These are per color channel snapshot. So every color channel is a snapshot result from the CMOS imaging system. These are some other examples that I'm sharing with you that are experimentally validated with the multicolor optical generative system. Phase encoding is very important here. And to showcase that, I'm comparing what would happen if you replace the phase encoding with, for example, amplitude encoding or intensity encoding for the diffractive processor. Phase encoding is performing the best. It's more diffraction efficient, and also it's generalizing better to red, green, and blue channels to give you a decent reconstruction image.
Dear Professor, we are out of time, so I will give you just a few minutes to summarize, okay? Thank you.
Sounds good. So arguably, one of the most exciting aspects of a diffractive optical generative model is the fact that you can multiplex information and deliver content securely to different observers, each of which will have a separate decoder. Because these decoders are static, you can think of them as variable systems as part of, for example, a smart display that you wear or a smart goggle. In this example, a digital encoder here is taking random noise and giving you a certain phase pattern. If you illuminate it with different colors and give different decoders to different people, everyone will be able to see from a single snapshot different images, so you can actually multiplex based on wavelength and decoder diversity, simultaneously transmit and multiplex unique content to different groups of users. This is great for secure and private communication to a group of users, generated content. If you don't do anything smart with the decoder, free space cannot do that. That's why you need these diffractive static decoders that are given. I can go over this maybe in the Q&A, but if you don't use a decoder, the system does not work as good as expected. And these are showing you some proofs of that. To conclude, diffractive processors give us some unique capabilities to process information through engineering of light matter interactions. Sometimes they can do all-optical classification, statistical inference, or solving computational imaging problems. But sometimes they also form powerful encoders or decoders to communicate information back and forth between digital and analog domains. So in that sense, there's a lot of room down there in terms of this collaboration between structured light, computational diffractive systems, and digital networks. This is my final slide. Thank you very much.
Thank you, Professor. So we have just a few minutes for 2 questions, maybe 3. So if any, please be active. Yeah, we have one.
Thank you for a fascinating talk. I've totally out of this field, so it's probably a simple question. How sensitive is the distance to the digital processor? So you had in a few of your figures kind of very specific distance in terms of wavelength. Is that very sensitive to the process?
Yes. So let me pick up one example. So yeah, so the layer-to-layer separation or input to diffractive layer separation. This can be sensitive, but the biggest sensitivity is not the axial dimension, but actually the lateral dimension. In other words, if there is misalignment between one diffractive layer to the next one, mostly spatially laterally, then you can have some computing problems, inaccuracy. We solve this problem by a process that is known as vaccination. You can look at vaccinated diffractive networks from our lab, published several years ago, as a way to solve this problem. And how everything that is experimentally shown in this presentation, every single result, there is a vaccination as part of it. We call it vaccination because the technique was invented by our team during the COVID pandemic. So that was the natural choice of the word. But the idea is simple. During the training of whatever you want to do, end to end, we on purpose produce misalignments. We produce lateral misalignments between this diffractive layer and this diffractive layer and this diffractive layer. At the same time, sometimes we misalign the object. We put it axially off or laterally off or shrink its dimensions. All of these noise terms that you input during the training they all make the system resilient to those kinds of perturbations. Of course, at the cost of some performance. If you want to retain the performance back, you have to have more degrees of freedom. So that's how we mitigate some of these misalignments, especially if we cannot fabricate accurately or align the system very accurately. Vaccination is a very important remedy for these.
Okay, thank you.
Hello, thank you for the lovely talk. I had a question regarding the vaccination itself. So what do you think would happen if you had a spectrally dispersive system where you not only had phase constant noise, but across the spectrum it varied?
So a lot of these examples are already, for example, if I go back to this problem here. So in this example, the diffuser is having a certain refractive index, but the refractive index is not flat for different wavelengths. For example, if you look at these output results from the smallest wavelength to the largest wavelength, you see some variation. By default, the system here is assuming that the random phase diffuser is going to change at different wavelengths. And that's why in its training, it's randomly changing the phase diffuser. But as a result of the refractive index at these different wavelengths being different, it's also learning basically how to reconstruct it in the presence of different spectral phase signatures that are random with a certain correlation length.
Okay, thank you. And the last one.
Okay, I have the question because in your first solutions you were using terahertz source and detector. So is it due to have less constraints on the diffractive optics you're using? And then following question is what's your technology for the passive diffractive layers?
So for terahertz, there are two major reasons that we started. First of all, terahertz waves can see through opaque materials. As a result, for certain applications, like for example, looking through an opaque object, like for example, this is a silicon wafer, right? And there is a defect within the body where standard infrared or visible cameras would not be able to see. Therefore, we were motivated by the fact that terahertz systems can see through ordinarily opaque objects and help us sense hidden defects. And that's why for these kinds of problems where objects are opaque and the defects or problems or whatever you want to sense is hidden there, there's nothing like terahertz. And that's why these are relatively bigger because the wavelengths are bigger. And that's why we're using terahertz systems here, just because visible infrared would not be able to see hidden objects. These are 3D fabricated with basically state-of-the-art 3D printers. These are mostly polymer plastic. Any design that you have in here, if you can fabricate this at shorter wavelengths, or if you can use spatial light modulators, you can use the same design. So for longer wavelengths, we're using off-the-shelf 3D printers that are used, by the entire industry. But for shorter wavelengths like infrared or visible, we are using 2-photon polymerization-based 3D printers where you can fabricate with a couple of 100 nanometers feature size with also a 3D printer, but based on 2-photon polymerization. These are not 2-photon polymerization, but some of the later results that we've got are achieved with basically, if you see this slide, this is a 2-photon polymerization-based diffractive processor. The size in here is a couple of 100 microns, and the features that you see maybe like here, if I laser point, this is fabricated by a 2-photon polymerization, 2 diffractive layers. These are the features here. And every feature here is on the order of a wavelength. And this wavelength in this case was 50 nanometers, so infrared. But this one is a terahertz, so it's bigger. The feature size is half a wavelength, which is approximately a couple of 100 microns. So depending on the wavelength, you have to switch your fabrication method from lithography, 2-photon polymerization, or standard 3D printing with PBS-like materials.
Okay, thank you very much. Yeah, I understand that it's never enough time, especially for the newest and emerging technologies. And as we saw, the papers were published just in the recent years. Yeah. So thank you once more, Professor.
Thanks for having me.